To enhance the predictive capability of our classifier, we implemented several feature engineering techniques. First, we bind continuous variables. We grouped ages into categories, which is child, young adult, middle-aged, senior adult, and elderly, to capture behavioral patterns across different demographics and classified BMI values into underweight, normal, overweight, and obese categories to reflect health risks. Also, we defined categories like low, normal, prediabetes, diabetes to differentiate metabolic risks. Second, we conducted feature interactions. We created interaction features such as age multiplied by BMI, glucose level multiplied by BMI, and age multiplied by hypertension to capture compound health effects. Third, we converted categorical variables like work type, smoking status into one-hot encoding to prevent ordinal misinterpretations. Given that the dataset had significant class imbalance, so we applied SMOTE to balance the class distribution. This ensured that the model didn't overly favor the non-stroke class, leading to improved recall and F1 score. When creating our classification model, we evaluated multiple classifiers based on their F1 score and business relevance in a loan approval setting. The matrix is showing here. Every model has its own strengths and weaknesses. First one is the decision tree. It can slip data based on feature thresholds, leading to high interpretability but overfitting to training data, which causing poor generalization. There was no significant increase in F1 score after turning parameters, so we didn't choose it as our main model. Second is KNN, which is classified based on the majority vote of nearest neighbors, making it sensitive to feature scaling and computationally expensive for large datasets. Changing number of n brought no significant increase in F1 either. Third one is the XGBoost. It uses gradient boosting over decision trees, which effectively handling nonlinearity and feature importance selection. So we chose this model as the base model. Fourth one is the Light GBM. It can optimize for efficiency using histogram-based slipping, but struggles with very small datasets. And the last one is the CAT Boost. We also considered CAT Boost further, which handles categorical data efficiently and improves generalization, but may not always outperform XGBoost on certain test sets. So after chose the model, we performed manual fine-tuning on XGBoost and CAT Boost. When turning XGBoost, we chose manual turning, as randomized search lacked precision and grid search was computationally expensive. We found that the turning on scale pulse weight plays a significant role. Then we applied feature importance ranking based on F1 score, selecting top 15 features, the most impactful feature set. As a result, after cross-validation, we achieved an F1 score of 0.3. Then we tried to CAT Boost to see if it could further improve F1. While CAT Boost achieved a higher average F1 invalidation at 0.3114, it performed worse on the cargo test set compared to XGBoost. So XGBoost could generalize better due to different tree structures or robustness to specific test set distributions. For model validation and fit assessment, as we mentioned, we use stratified K-fault course validation to ensure stable performance assessment and mitigate data leakage. Through the learning curve of XGBoost, we find that the model initially suffered from underfitting, which was addressed by increasing training samples and adjusting hyperparameters. The training F1 score, which is the red one, starts lower and increases steadily, converging with the cross-validation F1 score, which is the green one, as the number of training examples increases. The narrowing gap between the two curves suggests improved generalization, confirming that the model is neither underfitting nor severely overfitting. Additionally, the ROC curve shows an AUC of 0.8894, indicating strong discriminatory power. The curve is well above the diagonal baseline, confirming that the model efficiently distinguishes between positive and negative cases. Fine-tuning the probability threshold can help further optimize the balance between recall and precision. To future improve our model, we could utilize adaptive retraining strategies to maintain model robustness in production environments.